Welcome. In this session in linear data analysis, we'll state the spectral theorem. We won't prove it, but it's an important fact that we'll be using frequently. So let's suppose that some matrix C that is all real numbers and has m rows and m columns, suppose that it's a normal matrix. That is, suppose that C commutes with its transpose. The spectral theorem is that for such a matrix that we can factor it as, so it's not only diagonalizable, so it's not just similar to a diagonal matrix. Specifically, it is an orthogonal matrix times the diagonal matrix times the transpose of the diagonal matrix. We can see immediately that this makes a certain amount of sense if C is symmetric. It turns out that if C is orthogonal or skew symmetric, that this is also true. And let's restate this diagonalization result where we're specific. So it is that lambda is diagonal and lambda j is an eigenvalue of that original matrix C, and that Q is orthogonal. And when we say that this matrix is orthogonal, a whole bunch of things come into play. One is it has to be full rank. Another is that its columns have to be have unit norm. The third is that the columns have to be mutually orthogonal. So that is a general result. Now specifically, the symmetric theorem, and this is where we'll most often encounter the spectral theorem, is that if a matrix is its transpose, so let's say if a matrix is its transpose, then we have further restrictions, which are every eigenvalue is a real number, and that every eigenvector is composed entirely of real numbers. And what goes along with this is that if these are all real numbers and they are if they are columns of an orthogonal matrix, then that means that these, I should write that as a Q so that we're quite clear, is that every column of this is unit length, has a unit norm, and they're mutually orthogonal, which means that these constitute an orthonormal basis for the coordinate space of dimension m. Now, let's summarize what we've learned. We're now able to identify a normal matrix as one that commutes with its transpose. We can find the inverse of an orthogonal matrix by taking its transpose. We can state the eigendecomposition of a normal matrix using the spectral theorem, and we can characterize the eigenvalues of a skew-symmetric matrix as being either zero or purely imaginary numbers.